the contents of this webinar are, so we have 4 major points that we would like to cover during this 1 hour. So first I will give a short overview of what ELIXIR Compute platform is and the broader context on which this demonstrator is made. So after I finish, Ilkka Lappalainen, also from ELIXIR Finland, will explain what the human data use case that we are supporting with the more technical functionalities really is. Ilkka's presentation, so we will go even deeper to the technical details with the presentation of Alexander from EMBL EBI, and then Juha Törnroos, visiting ELIXIR Spain from ELIXIR Finland, will do the actual demonstration. So we hope to finish about 10 minutes before the hour is due, so that we could have a short discussion of what ideas or questions may have arisen. So first a little bit about the ELIXIR Compute platform. So you could say that the big picture is that we would like to provide an access to distributed resources, data, clouds for the users from the viewpoint that once you have a European identity, there would be a way to access different services with that single identity. So we are running a service that enables this, and the idea would be that in the long run, a researcher could use their electronic identity provided by a trusted party like ELIXIR to create scientific software environments of their liking on the target clouds and use the environment to process large biological data resources that are also maintained by the ELIXIR infrastructure. So this is a key functionality of ELIXIR that will be talked about in several places during this webinar. So the focus of this webinar is how we use the federated identity to link together data access rights, the transfer of data, and access to a cloud resource where those data could be processed with the chosen software environment. So ELIXIR is a fairly large research infrastructure already, so it combines 21 nodes across Europe, and many of those nodes are long-term research service providers, and their combined capacities to support life sciences, computing, and data management could be comparable to other major fields of science. So if we just count together 7 nodes from these 21 with the confirmed cloud capacities that they are more or less dedicating to life sciences processing needs, we get 60,000 cores, 24,000 terabytes, and 3,000 users. So this is the scale of the physical infrastructure underlying the different processes that we are talking today. And the aim of the ELIXIR Compute platform is really to integrate across the different capacities and functionalities of the platform in order to support the scientific communities. So this is the technical community itself is a fairly large and complex environment, but if you combine that with the different high-level scientific goals, so you get a very complex integration task, and this is what the ELIXIR Compute platform is investing its resources to. So we are not doing this alone, or we can't. Basically, we have to position ourselves between the relying services, like the European Genome-Phenome Archive that is part of the demonstration today, acting as a translator for also the external service providers like the European e-infrastructures. So the ELIXIR Compute platform supports the different use cases by providing expertise how to utilize things like the GÉANT network and the trust framework that they are running to identify researchers in Europe. Scientific use cases are also important, as I said. The technical community itself is pretty wide and self-consistent, and there are many interesting developments taking place, for instance, in the cloud technology. So we use scientific use cases defined within ELIXIR to drive the technical development. So we have done a demonstrator already for the metagenomics analysis pipelines. And what we do today is that we will dig deep into what we are doing in order to enable human access control data to be transported from the European core data resource into a secure cloud. So I think I will stop my introduction there and give the presentation next to Ilkka Lappalainen from Finland. So Paris says goodbye for a while, and Ilkka, are you ready to take the ball?
Yes, thank you very much.
May I ask Prem if you could? Yes, thank you.
Thank you. So, thank you, Tommi, and good afternoon to everyone on my behalf as well. My job here is to drop you more into the human data use case, and what you can see here today in this slide is the current research environment in many places in Europe, where the researchers in the center place and they contact the local biobank and access samples, or in some cases maybe even data that's already been generated from those samples, and then they need reference data from European Genome-Phenome Archive. And in both cases, they have to go to a data access committee, which is the DAC in this slide. And this process is sometimes even in a paper-based application. The data access committee then grants access to the data, which can be hundreds of terabytes. And at least in Finland, they will most likely then upload the data to the ELIXIR node, which is in the left-hand side of this slide. So the researcher has to do everything in there. Well, how do I move forward? There we go. So the question is, how can we provide a secure and easy access to the data for the authorized researchers and help them along the line? And so this use case aims to provide a discovery service for the researchers that combines the local and the international reference data, where they are and how can they access to it. Then to provide an electronic way to apply access to the data. And most importantly, store these data access decisions in a way that they can be used in the underlying systems for controlling access to the data. It should support secure data transfers at scale, and it should provide economical solutions to manage the sensitive data in ELIXIR nodes. So if you have 5 use cases on the same data, not to replicate the data sets 5 times locally, but to somehow use the single copy of the data in a reliable and secure way. Enforce data access permissions for each researcher that may be sharing a virtual machine with another one. And then most importantly, to create open source, industry standard container solutions where possible, so that we can provide portability across the ELIXIR. So what you see today here is something we implemented in EMBL EBI and CSC to ELIXIR Finland. But this should be a solution that can be replicated to other places in Europe. Now, this is the summary of what we've been building up, and I walk you through it, and we come back to this picture many times during this presentation. Up there is the researcher, and if you go to the right-hand side, then they apply access now electronically from the Data Access Committee using a tool called REMS. It's developed in Finland and can be applied across the ELIXIR for different type of services that require data access control. And in this case, we've applied it with the EGA, so we've integrated it with the EGA data access control as well. So in this case, the researcher can use REMS to apply access from local biobanks that hold the data in CSC in cold storage, which is in the middle of the picture, or they can apply access to datasets stored in the EGA. And when the data is under the EGA umbrella, importantly, the data access decisions are fed into the EGA, where the master database is. And I will show you a couple of slides now before coming back to and explaining more about this overall picture. This is still under development, but this is something you would probably see as a researcher in Finland, hopefully in other nodes as well. So, and the left-hand side is something that is specific for the user itself. In the middle is a catalog of data resources that are held already in Finland. They might be local data sets from the biobanks or some other genomic data sets collected from the cohorts, national cohorts here. And then there's a complete archive that goes to the EGA and to the central biobanks. And if I click on my orders, it would show something like this. So here are the active data sets. They are being, one of them, the first one is completed. It came probably from the EGA itself. This is all just as an example. And the second one still being transferred, so 150 files from the 800 have been successfully transferred already to Finland and are waiting here. And the third one is still pending. And the second table shows the process of applying access to other data sets. So the user can manage their view on what is actually being ordered from the central repository to Finland and what is the status of those data sets. And that's the way they can control how they access the data then when they are ready for the usage. Now, before going to look at how you would access the data, it's also important to look at what actually happens in the data transfer from the EGA to the secure storage. So the line from the EGA on the bottom of the picture to the secure storage. And so at the moment, we're restricting the services in a way that they only managed by the node, and they only happen from the central archive to the node rather than between the nodes or the researchers transferring data from the node to the node from the central archive. And this is to make sure that we are operating in a secure way when we do move this into production, and we only copy one copy of these data sets from the central archive. And the way we've done this is that we've added security on top of the compute platform supported transfer solutions. There will be many of these protocols that the compute platform supports, but currently it's been tested with the GRID FTP, and we also show you in the demonstration the latest upgrade to use a Global Alliance for Genomics and Health standard called the HTS GET. And just to make sure that what is actually happening in these data transfers is that the blue boxes here are CSC in ELIXIR Finland, and the red ones are the EGA in Bolivia in this case. And so the CSC would, on behalf of the researcher here in Finland, authenticate to the Bolivia EGA services, present a download request. The data would come from the archive where it's encrypted, the through a fuse layer to a grid FTP. So this is how we are providing more security on top of this data transfers. And while it's been transferred over the internet to another grid FTP service here, hosted here in Finland, it goes into the staging area, and it's encrypted with a key that is CSC public key, and only we know the private key. And so while it's been transferred over the internet, it's encrypted for added security. We then re-encrypt and validate each file before we provide it to the researchers. So it's rather complicated when the number of files transferred goes into thousands and the data size goes into hundreds of terabytes. So how does the user then log into the virtual machines that are shown here in our secure e-portal and access the secure storage, which is on the left-hand side on this picture? So our cloud is infrastructure as a service, and this means that we virtualize basically more resources to the institutions that are here in Finland and add their capacity to do genomic research. And because of that, we have to think hard how to provide the security, as we don't manage actually the user accounts in the virtual machines. And there's two of these models that we try to think in the beginning how should we do this, because we want to restrict the access to the data per researcher and not on the virtual machine. So if in the left-hand side there's a model where one researcher uses their own virtual machine, and of course that would be fairly easy to control the access to the data at the level of the virtual machine, but most of the researchers actually want to share the virtual machines and work as a group. And so we clearly separated the authentication from the authorization. And the authentication is managed by the host organizations, the University of Helsinki, for example, whereas the authorization is now accessing through servers that we manage as a hosting institute for this service. We can harden the security levels, and we can control what kind of software is running in these servers. This will become more clear in the demonstrator later in this talk. And just to show you, the last slide this is actually how we enforce the data access permissions. The workflow starts from the right-hand corner and up and goes towards the left and lower part of the picture. But the main point here is that the user authenticates and receives the authorization to use a particular dataset in their virtual machine. And I will leave it to this, and I think Juha will come back to and explain it in more detail as part of his demonstrator.
Thank you, Ilkka. So the next speaker is Alexander from the EMBL EBI, and he will dive even more deep into the underlying technologies at the level of the microservices, for instance, that are the functional components of. Alex, you're online? Alex? So Alexander, we can't hear you, at least I can't in Paris.
Looks like he's muted, I think.
Okay. Now it's much better. Can you begin from the beginning, please?
From the beginning. So I am Alexander Senf. I work with the EGA archive team at EMBL EBI, and I am essentially responsible for providing access to EGA data to authorized and authenticated users. So my presentation today is outlining the technology I've developed for that and showing how that can be used to replicate the access mechanisms and the access permission enforcement across multiple nodes. So I'm diving straight into the technical details of what I'm doing. So the access API that I have written on the back end has been implemented using a specific architecture that is called the microservice architecture pattern. And essentially, this means that we're taking the functionality that is necessary and separating it out into individual small units, which can be independently developed, independently deployable, easily scalable, and which talk to each other using the HTTP or HTTPS REST protocol. At the EGA, we have identified these key functionalities. So there are microservices that implement each of these, and I will talk about them in a little bit. But essentially, there is archive cryptography, there's a database interaction component, then there is the metadata and data access components for the front end, and then there is a bunch of environment-related services. So there is a router and a filter, and certain other environment-related services which make this system as a whole work better and more scalable. The technology I've chosen to implement this is standards-based. So everything is written in Java using the Spring Boot and the Spring Cloud frameworks. And within Spring Cloud specifically, I make use of the Netflix open source stack components. So the backbone of the system essentially is similar in technology to what Netflix uses to stream data across the internet. This allows me to use certain services. First of all, there is a configuration service. So each microservice has absolutely no configuration service of its information in the source code of its own, which means all the code can be open sourced and freely available to download. The actual configuration is hosted centrally on a configuration server, and the microservice, upon startup, automatically obtains its own initialization from that service. Once a microservice has started, it registers itself with a discovery service. That means it then is known to all other microservices running at the moment what is available. And if they want to communicate with each other, this service also resolves the name of a microservice to an actual URL. So if I want to talk from one microservice to another, I merely specify its name, and this service resolves it to the actual URL. The advantage here is that if multiple services of the same name are running, I get automatic load balancing across these microservices. And finally, there is a circuit breaker pattern implemented. This monitors all the interactions with all the services. If it notices that a circuit appears to be broken, it can provide fallback options and so prevent cascading failures. And as an added bonus, provide very detailed logging, real-time logging information. So regarding the actual functionality, first of all, I tried to write this in a way that it is portable. So I have written two abstraction layer services. First of all, we assume that the archive that holds the EGA data, the files are encrypted in this archive. So I need to find a way to obtain the archive encryption key before I can access the data. And so one microservice merely abstracts the local key management service you have chosen so that it can provide a standard API that the rest of the services can use. And secondly, there's a few databases that contain information about files, file names, file paths, etc. Again, here I'm providing a standard API to the microservices, and on the back end, you can customize that to your local database installation. So these are just two services that improve the portability of this API. The biggest component of this API is a cryptographic service. This is the point where the file is accessed by the API. This then also abstracts your backend storage technology. For example, we are using an object store at ELIXIR. There is a file system at CAC, but they're all accessed the same way on the other end of the service. This service handles random access queries, so the encryption technology that is used for the secure storage of EGA files allows us to randomly access a file and decrypt just portions of it. As an added bonus within the API, I can access files by ID as well as by absolute paths. So if you want to just access file with a specific EGA file ID, this service will understand and find this file. And then on demand, it decrypts and encrypts the data streams as you request it. So this is basically the engine that provides the data for the users. Then there are two edge services, which means they are part of the publicly accessible API. As edge services, these two services enforce user authentication and authorization. One of these two services provides metadata access, which at the moment is a list of the data sets to which you have access, as well as the files within these data sets. But in the future, there will be other metadata that will be added onto this list. And the second of these components provides the actual data access. So here you request a byte range of a file, for example, or request a genomic region, and it will return the actual bytes corresponding to that, encrypted in various ways or in however you have requested it. This is then tied together by a front-end router or filter. Again, this is using the standard Netflix open source stack pattern. This allows me to take multiple backend microservices running on multiple ports and combine them into a single API. It performs automatic load balancing. It allows me to shape traffic according to certain rules. It allows me to do retries to increase the stability of the API. And in my case, there's also some value-added functionality, which will allow me to integrate ELIXIR AAI authentications into the system as well. I will talk about that in a little bit. Schematically, then it looks like this. On the bottom is where the actual request comes in. It is handled by the filter component and routed to either the metadata and the data component, which then most likely accesses the database to get some file information, and then through the cryptography component accesses the archive itself. The configuration, discoverability, and analysis on the right-hand side then interact with all of these services. The deployment is meant to be very flexible as well. And just to show an example, here at EMBL EBI, this API currently has access to about 112 CPUs distributed over 5 Linux servers. We have the API front end triple load balanced. The data path on the back end is double load balanced, and they're deployed on the plain Linux servers. Compare that with the same deployment at CSC. Here, microservices are Dockerized, and they're orchestrated into a deployment on Linux VMs. We are hoping to work towards a system where the whole API can be very easily orchestrated into a Kubernetes or Docker Swarm type setup, where it can automatically grow and shrink based on demand. Now, the second component, we decided to separate that out from the actual functionality of this API, is the security aspect. So here, we again went the route to use standards-based technology. And the route we went in this case is to use the OpenID Connect OAuth 2 standard. So at the EGA, we are running an AAI service, an authentication and authorization infrastructure service that provides OpenID Connect tokens authenticated against the EGA user database, and which provides authorization information upon demand against the EGA permissions database. The data API, so the data and metadata services, validate tokens against this AAI. So there is one of these EGA AAIs running against one central EGA user and permissions database setup, but there can be multiple data APIs which all connect to the same AAI service. So regardless of where the API is running, all the permissions are always enforced uniformly across the entire EGA space. Being also an ELIXIR node, we also needed to implement or integrate this solution with ELIXIR AI services. We did that first of all by using the same underlying source project to implement the AAI. So both ELIXIR and EGA use the same project as a base built upon. The only difference that now exists between ELIXIR and EGA is that ELIXIR can authenticate an ELIXIR user, but has actually no idea who that corresponds to within EGA or what that person's permissions are. So I added to the Zool filter the functionality for an ELIXIR token to be mapped to an EGA user, and then the permissions of that EGA user to be injected into the REST call before it is forwarded to the API. The reason these two things have to be separate at the moment is merely because at EGA, we get the user accounts from the DAC data access committees, and we cannot force them to send us ELIXIR users to provide access. So there will always be a small pool of users with no actual ELIXIR connection at all to have access to the EGA archive, even if a lot of users will have ELIXIR ideas. And the solution is to allow users, essentially, when they have an EGA user account, to map that to an ELIXIR user account. So this is a call that a user can do. And once that mapping has happened, that user can log into ELIXIR and access EGA in the same way as they can log into EGA and access EGA. It works identical. And the demonstration later on will show you that there's absolutely no difference. So getting a bit more specific about what we have implemented in the first instance between EMBL-EBI and CSC. This is just a schematic of the API that is deployed in both locations. So at EMBL-EBI, the entire API that I explained is in the blue box. It attaches to the central EGA archive, and it gets permissions and authorization information from the central EGA AAI service. On the right-hand side, we have the identical code setup running at CSC, connecting to the same ELIXIR service, connecting to the same central EGA AAI, and then they have a local EGA storage. So regardless to which node you go, you can log in, get single sign-on between both nodes, and access data either at EGA Central or at a local EGA such as Finland. The API itself then, it provides various ways to access the data. First of all, it is an HTTPS REST API. You can use REST calls to download whole files. You can specify byte ranges of files to be downloaded. Or you can now also specify genomic coordinates from specific types of files, from BAM and CRAM files specifically. Another access method is the fuse layer, which I will talk about in the next slide. And here we have two methods. One is to run the fuse layer locally and then attach a grid FTP server to it. This is what we use for replicating data. It is also possible to attach an Aspera service to it. So this allows you some standards-based access methods to the EGA. And on the right-hand side, it is also possible to run the fuse layer locally in your system. And that way, the EGA data then appears to you as a file system. So what that means is a fuse layer essentially is a virtual POSIX-like file system. So the data is hosted at EGA, but what you see in your local system when you start the fuse layer is just a directory. It's a folder, and there are files in that folder. As soon as you access a file in this directory structure, the fuse layer translates that into HTTPS REST calls to the EGA API, which then returns the data you requested, and it delivers it to you as if the file was locally on your disk. Essentially, it gives you a disk, a directory view into the EGA archive based on your permissions. And we have added a lot of caching on the local end to it to improve the performance to adequate levels in this case. And if you look at this whole stream of the data from the archive to the actual end user, it goes from an encrypted archive through cryptographic microservices that change the encryption format, through the REST API services, which control your access and authorization via some sort of network to you, to the end user, where there's a fuse layer running or where there's an analysis pipeline running. And with this, I should hand it over to Juha to actually do the next bit of this presentation.
Thanks, Alexander, and greetings from Barcelona. Next, I'm going to give a brief introduction about the setup which we have at CSC. We have actually deployed this solution to our production environment, but it's not in production use at the moment. And that means that we are running it in production hardware, but we don't offer it to our customers. We are planning to start piloting the service in the following months. And at the moment, this service runs on separate hardware, and the only connection to ePortal Cloud is via network. And data is mirrored from EBI, and this is actually a task of Accelerate Work Package 9, large-scale data mirroring. And data is stored in NetApp's storage solution, which offers POSIX-compatible interface to files. And here is actually difference to EBI. EBI uses CleverSafe object storage solution. And this picture explains the current setup. So there is two customers in ePortal, a green and blue one, and these both customers have virtual machines in ePortal, and they can access to this storage via this gateway, network gateway. And if they want to connect to internet, they have to do it from their own network. So there is no network connection to internet from ePortal at all. And we have two different servers. One server is connected to internet, and that handles connection to central EGA and to ELIXIR AI. The other server, which actually runs the API, is connected to ePortal, and both of these servers have a connection to storage. And users are authenticated using ELIXIR AI, and data use permissions are fetched from EBI. And that means that the user authenticates to virtual machine with his own credentials. These credentials are usually provided by his home organization, and then user authenticates to ELIXIR AI inside the virtual machines, and then he or she authorizes the fuse file system access the data. And this fuse file system passes ELIXIR AI access token to EBI, which then verifies their permissions. And I'm going to demonstrate a demo video. It's going to take some time to prepare this.
While Juha prepares the video, so okay, now it's coming up already. Never mind.
So at first, user is going to create a virtual machine to ePortal Cloud, and this can be done, for example, in this web user interface. And now user is launching new instance, defining a name for the instance, and selecting an image. And now user has a virtual machine ready, and he or she is going to SSH to virtual machine. And now user is going to authenticate to ELIXIR AI. And user is going to also authorize the fuse. And now user is able to access all data sets which he or she has access to, or permissions. So there is only one data set and only one file. And user can read the file. And user can access to content of that file. And things like encryption on the fly is happening at the same time. User doesn't have to care anything about that kind of things. And now I'm going to hand this back to Alexander.
Okay, thank you. I just wanted to add on to this fuse layer presentation by pointing out that there is a new API that is being developed at the moment. So in the context of the Global Alliance for Genomics and Health, we have there is a development towards a standardized way to access genomic files. At the moment, these files include BAM files and CRAM files, and we are almost ready to also include VCF files. So the idea here is to provide a standardized way to access these files via API so that they don't have to be downloaded first and still can be supported by standardized tool chains and browsers, etc. The HTS protocol essentially works according to this picture here by making a request, specifying a file, specifying a genomic range, selecting filters and tags to in and exclude. And this lookup indexing service then returns an array of HTTP or HTTPS URLs and any header information necessary to authenticate into these locations. These URLs are then downloaded and assembled locally into a file. This can be done on the file system or in memory, etc. But then you have essentially a subset of a genomic file that you requested originally. This is an API that has now reached version 1.0 at the last GA4GH meeting, and it is already supported by a large number of people. So the ENA, EGA, and European Variation Archive support it in their APIs. SAM tools, part of the HTS-lib set of tools, they can talk directly to HTS-GET without having to download data. There are servers and clients available from DNA Nexus, Sanger Institute. It is now also part of the Google Cloud platform. So if you have genomic data in Google Genomics, it provides you access to that via HTS-GET, and it will soon also be added to Genome Maps. So this is just a quick looking forward of what is available in the future as far as genomic files are going. And with this, I'm handing it back to Tommy, I think.
Yes, thank you very much. So this was quite a load of technical information. And I'm hoping that we would spend the rest of the webinar, which is approximately 14 minutes, to discuss and ask questions. So in addition to the presenters, so we have people online who know about the secure cloud setup, Jaakko Leinonen, and we have our Spanish colleagues Oscar and Angel online who know more about the use cases that would be relevant for this kind of underlying technology. I'm just browsing here, so I see that there's also Thomas Keen and Jordi Rampla. So I think we have fairly good people here who know details of everything that you have heard. So if there are any questions that somebody would like to raise to discuss further, that would be most welcome. Anyone? So if nobody wants to volunteer, so maybe I could ask maybe Thomas or Jordi, would you like to add something to what was presented from your viewpoints?
Sorry, I just got disconnected. I just couldn't manage to get back on again. How far have we got to?
So Thomas, we are now in the discussion phase, and I was just asking for anyone if we were completely comprehensive or if somebody would have wanted to ask something. And I was trying to toss the ball to you and Jordi if you would like to add something for the things that were presented. So maybe you could tell a little bit from the EGI archive viewpoint that how does our little exercise go forward, or how would you like to see the next developments, or what sort of things would you like to see?
Yeah, sure. I mean, I think the key point from this demonstration and the technologies we've used and the fact that we're joining with ELIXIR and using the Global Alliance for Genomics and Health standards. I think the key point from the EGA is that we want interoperability, and as Alexander said, I mean, by leveraging some of the standards that are being developed, in Europe and across the world with GA4GH, I think this HCS-GET implementation is a really good example of how we've immediately got interoperability with several other platforms, and the same interfaces being offered by several other servers and services, and that are on the slide and that's on the screen. And I think this is the way we want to go forward, certainly from EGA, is that we don't want to build standards, or we don't want to build implementations or standards that are EGA specific. I mean, the future for EGA is federation and it's interoperability, and I think ELIXIR is giving us a platform for that, and GA4GH is also giving us a platform, and HCS-GET, I guess, is the kind of first example where we think this is kind of potentially worked quite well, and hopefully it'll be the I think for the AAI that was talked about. I mean, there is recommendations from GA4GH, and certainly what we do in EGA should be totally compatible with the GA4GH security group recommendations, which I think are compatible with the ELIXIR as well. So, we want interoperability on the AAI and interoperability on the streaming of data, and I think I hope we've kind of achieved it through this this demonstration.
Thank you. So
Hi, Thomas. Sorry, Tommy. This is Jordi.
Go ahead.
I don't have too much to add, but just to highlight a couple of things. One is that from the demo, we see that the process is quite easy and transparent for the user, but from the previous slides, we have also seen that the background components and hardware that it's behind that, it's not trivial. It's not just one server with a single service that it's providing all this stuff. That we have a redundancy, we have a scalability, we have plenty of things that are of value having in a software deployment. This is one thing, and the other one is that, in my understanding, although there are initiatives around the world for providing these kind of services, they are mainly internal solutions with internal number of partners that are trusting one each other in a proximity way. In our case, I think that we are having one of the first intent of doing something that, of course, initially is for a reduced set of partners, eventually is created with the openness in mind in order to make this very, very transportable to many situations. Okay, so I think these are these values that we should highlight on the solution you have just presented, and that's all.
Thank you. Would anyone of the participants have something to add or comment or ask? I could also, yes.
I have a question about how do you validate that you've got all the files and the complete files, things like that? Are you using like Git or the manifest or something like that to verify it?
Would that be Juha or Alexander? Or Ilkka?
Oh, okay. So at the moment, it is validated against the metadata API we provide, actually. So the metadata API lists all the files that are available in a dataset. If you download it, you would validate file by file as you receive it, that you have the whole list of what was originally in the dataset. So it's not an overly automated process yet. But
I was thinking mainly because it's been going back and forward through encryption at all the times and things like that. Have you got one that can verify from start to beginning that it's all okay?
Hello, can you please repeat the questions? There was some noise in the background, or we didn't really understand. We didn't really hear you.
So I think I can try to summarize. So how this currently verifies that the files have been transferred from EGA Central Archive to Finland is that we calculate MD5 checksums at the EMBL EDI for each file that we're transferring over, and then we calculate them in Finland as well. So we validate each file whether the transfer itself was correct, and then we also calculate the MD5 checksums for the unencrypted file, so we know that the file is intact. Now there are some protocols that the compute platform is working on which will automate the dataset replication. As Alexander said, at the moment it's based on transfers based on the metadata that describes the dataset. So we hope to test the compute platform solutions later this year or early next year.
Any other questions? Anyone?
Hello, everybody. Salvat speaking. I would like to know how far are we from using this system, the Fuse system and so on, in platforms like Galaxy and so on to run full workflows?
Go ahead, please.
Yeah, so basically, if I understand the question right, is like when would the software be having the interfaces to use the underlying infrastructure? Or maybe Alexander, if you understood Salva's question better, so you could please just go ahead.
So the API we have demonstrated is very near being completed. So it is running at EGA at the moment, but it is not running publicly, so to speak. And we hope that by the end of this year, we have a production level deployment of the API at EMBL EBI, and because the same code is replicated to each individual node that uses it, they would get the production level code at CSC, for example, as well. The Fuse layer then is already pretty much ready, because all it does is it provides a file system view of the files. And so the main component here is the interaction with the API. So the main component ends up being the API, making sure that it is stable and scalable. And so yes, the hope is that by the end of the year, we are production ready with it.
And just to add to that, so we've demonstrated that we can stream data from the EMBL EBI and from our local storage here at CSC to ePOTA using the new ATS-CAT standard and the new samples, and drop down a BCF file. So it is true that we can use it, that it opens up a lot of different options that we can use it for. We haven't tested it for a real workflow yet. And maybe Alexander could talk about the trade pilot where you have actually managed to connect a Galaxy into the EGA backend, although it's not exactly using the same infrastructure that we described here, but similar.
Yes, so this trade pilot integrated EGA essentially into a production research pipeline. In this case, the data was downloaded from the previous version of the API that is currently running here. So data was always downloaded from EGA into the secure Galaxy Cloud location, then decrypted there and used directly. So this is sort of a workflow that has been demonstrated that it works already. What we are trying to do with this new system is that we cut out the need to download a file, but only we can integrate the archive directly into the production pipeline, so that there is no need to download and decrypt data locally. You just point it to the API or just start the Fuse layer, and then analysis runs on that component.
Thank you very much for the answer.
This is Yanni from Basel. I'm curious to know what kind of performance you have with this Fuse approach in accessing the files.
It's a good question. So we have added cache pages to the back end of the Fuse layer. So when you first access a file, it downloads multiple cache pages around the region of the access you're performing in parallel on the back end. So for most cases, when you access a file, either linearly from beginning to end, or if you access it without jumping around too much, you basically access data in memory, which is fairly fast. Only if you jump around from the beginning to the end of the file a lot, that would introduce an overhead where the pages have to be loaded at the point where of the access, and they can't be preloaded. But overall, we have seen, and that is a non-technical term, we have seen good performance. The technical analysis and the performance analysis will follow, and we'll publish that as well. So at the moment, I can say it's a decent performance for the system that we're seeing. Certainly something that is usable in an analysis.
Thank you.
Tommy, we cannot hear you.
Hello, can you hear me?
Yeah, now it's better. Yeah.
Oh, okay. Sorry. So so you have missed my conclusions.
Yeah, basically the last 30 seconds or 20 seconds we didn't hear.
Okay, so basically, so the discussions can continue offline. So there has been now virtual introductions to people who know about the technical details and also the broader side. So if I may, I would like to conclude this webinar hour with a few points. So I think we have demonstrated that the automated and secure and a scalable data transfer between the main archives in ELIXIR to ELIXIR nodes is feasible, but it's not trivial, as Hordi said. I mean, this is something, if we automate this for the end users, they might not appreciate the complexity of the different interfaces and integrations that Alex and Juha and the others have achieved. But this will be an important thing to do, since human data processing will grow in volume in the years to come. So one thing that I think is also very important is that if we encapsulate the scientific software pipelines, like automations that Salva said in software pipeline, so we increase the portability of the analysis that researchers develop, and also this containerization can increase security if the data is analyzed on safe platforms. So what would need to be done is that data transfer access methods like the data streaming that were demonstrated, so that the software gets the data. So there's an interface to input the data to the scientific software. So this is something that we probably cannot influence. So the software developers themselves have to see the technical opportunities that are coming for them. So what we want to do in ELIXIR is we want to enable really computational access to data, both the local institute users and the international users. And reference data that ELIXIR collects is vastly important for making the right analysis for life sciences. So in the next years to come in Europe, we expect that in the compute platform we'll be setting some of the examples what is needed by the life sciences data analysis. So we need to already start thinking that if this is part of a European science cloud, so how do we manage all the different user identity authorization and cloud access decisions? Since the security will be required, it will become as part of the general data protection regulation that will be enforced next spring. So we have to, as data processors, we have to respect these regulations. So with these words, I would like to close the webinar. I thank you all for attending. I think we had around 40 participants, so we highly appreciate you to come to listen to where the work is going, and we will continue from here. So thank you very much for your time. And then virtual applause.
Thanks.
Thank you. Thank you.
Bye.
Goodbye.
Thank you.
Thank you.
Tommy, it's just Prem speaking. Just as Tommy said in the beginning, the recordings from this webinar will be available online on the ELIXIR website in a few days' time. And last thing, on Wednesday this week, there will be another ELIXIR webinar. It will be on identifiers.org. The webinar is already on our website, and it starts at 2 o'clock UK time, so 3 o'clock Central European time on Wednesday this week.
All right. Goodbye.
Thank you.